And there's one that's made me rather famous called unusual disk latency. And these spikes in latency were caused by that video. How many people have seen this video, shouting in the data center? I'm checking if has anyone not seen this video? Wow, a few people haven't seen it. That's good. So what I'll do is I will tell you how this came about, because that's not in the video, and then I'll end the presentation. If you haven't seen it, I'll play it at the front. How this came about, because I know most of you have seen it, I was doing performance analysis. When we released the Sun Storage 7410, I wanted to print some basic numbers: streaming disk read, cached read, streaming disk write. I was performing the test of streaming disk write, and the numbers just weren't what I was hoping. I was expecting a particular rate of performance, and it was just a bit less. So I was poking around to try and figure out what had gone wrong. Maybe a disk had died, maybe a cable had fallen out, it was only doing single pathing rather than dual pathing. And I saw that latency was particularly high some of the time. I broke it down by disk, which you can do in analytics, and it told me that a single disk had bad latency. I was like, good, all right, fine, I've got a bad disk, time to toss it out and replace it so I can do my write benchmark. As an aside, this is a problem we're starting to run into a fair bit, where disks can exhibit bad latency but not give you soft errors. This is really frustrating. We'd prefer, if a disk was going to perform badly, it give us an error so that we can deallocate it from the ZFS pool and pull in a working spare. So hopefully we'll talk to the vendors and try to get them to... I don't know why they're not sending errors. Obviously something's going wrong because the disk has started to respond very badly, but they're just not telling us that. We could be clever and try to write some dtrace that said, if the I/O latency is 2x the standard deviation, it would be much easier if the vendor just gave us a soft error to say, yeah, I know I'm in hell. I'm giving you 50 millisecond reads rather than 5. And then ZFS can do the right thing. So I had this issue. A disk was giving me bad latency. I go to yank it out and replace it. And as I take it out of the slide, I notice that it's missing one of the screws. Adam Leventhal had run into this before, where when you have a JBOD full of disks spin fast, you've got fans in there, things vibrate. That's fine, they're designed to handle that. Part of that design is the disk drive brackets need all 4 screws to hold them in place. If they're loose or you're missing one, they can actually wiggle enough to cause a vibration issue. I thought, wow, this is really cool. Analytics has identified a disk, has identified a missing screw. This would make a great blog post. So I get my camera, I go back in, I put the drive back in with the missing screw, I reapply the workload, nothing. Everything works fine. It's like, no, please, this is the point where I want you to perform badly. I want you to vibrate right now. I tried different workloads, I left it running for ages to replicate the issue, because I really want to have a nice blog entry. You know, analytics identifies missing drive screw. It just wouldn't work. And so I was thinking about it and thought, well, maybe the disk had shuffled into a funny location where it was more sensitive. So I put my finger in and I bumped it a little bit. Nothing. Fishworks is next to a bus stop where buses drive by and they're really loud. Maybe a bus drove by and shook it. So I'm kind of shaking the JBOD and patting it and trying to give it a bit of extra vibration. That didn't work. So maybe it's louder than that. Earlier that day, we had the alarm system in our server room go off. This is the alarm system that puts gases in to contain fires, the FM200. It had developed a situation where it had a system normal alarm. I don't know why they programmed a system normal alarm, and it's really loud. Of course, being a room full of engineers, we have we try to have such logical conversations with the repairman. Why does this have a system normal alarm? Anyway, that thing was really loud. So it's like, maybe it needs to be loud. That's when I got the idea of shouting at it, where I could shout at it to replicate the problem. So I shouted at it, I had a look at analytics. Hooray, I finally rattled that loose disk. Then I had another look and realized I'd rattled all the disks. So I put the screws back in, made it back into a normal JBOD, and shouted again just to be sure the latency was there. So I ran and grabbed Brian Cantrell and said, "You've got to check this out. This is amazing." And when he saw it, he's like, "That's it." Because I had the camera, because I thought I was going to take a few photos for a missing screw blog post. He's like, "Does that thing video? Let's do a video and stick it on YouTube right now." So we had it on YouTube in less than half an hour. And we thought, this might be fun. We might get 1,000 hits. Last time I saw it, we were at over 500,000 hits. And I think it's the most watched Sun video on YouTube. Or anywhere. And it's completely by accident. No offense to people like Deirdre who work on Sun Video and work hard. We just had the luckiest event of our life. So it's amusing. If you haven't seen the video, I'll play it up here in a moment. So you get to see that. Shouting in the data center. It's not a vibration problem. So the question is, has anything been done to solve the problem? I was shouting pretty loud. I took in a decibel meter and it just maxed out the decibel meter. So I don't think I have superhuman shout capabilities. I just think that you can shout really, really loud, much, much higher than the background server and noise. So we haven't had any customers say that the background noise causes this normally. And our server is pretty loud and it hasn't happened. So we don't actually think it's a problem. We have had some few comments about it. Some people thought it was a hoax. It's like, why would I hoax this? I got a bunch of emails from disk vendors who said, yeah, we've known about this for ages. Like, this is a known problem. And fair enough. I guess no one thought of, or maybe they have shouted at it and seen it before. We had some people tell us, this is terrible. You've demonstrated to the world a weakness in Sun's JBODs. It's like, it's not a weakness in Sun's JBODs. It's disks. Any disks would do it. And people complained enough that we actually got a competitor system, which I can't name, and they're expensive fiber channel disks. And I shouted at that. Had to dig through their interface to figure out how to measure disk latency. It wasn't as nice as analytics. And we replicated it. We didn't want to replicate it because we were trying to argue with these people. It's like, believe us, we know what we're doing. It's not a problem with the Sun boxes. It's a disk issue. But it just reached the point we just had to do the test. We didn't blog that because I'm so sure the other company wouldn't like it. And we don't need to either because it's a disk property, not a JBOD property. So that was a lot of bad things about performance. There were various lessons to learn from this, and often gaining experience in performance is about making mistakes and learning from them. I've never given a presentation like this before, and of course my habit is I have the habit of wanting to talk about exciting, awesome performance numbers and tools, but it was lots of fun to think about this and write it up. And I'll get the slides online, and I'll also add some more examples to this the more I think about it, because we've wanted to do it for a while, to talk about bad things in performance as a way of educating the field. It's just tricky because we can't actually name customers or vendors apart from ourselves, but I think it's a good thing to learn from. So that's the talk. Thank you for attending and braving the snow. And if you haven't seen the video, come out to the front. And do we have? Are we handing out any books? Is that happening?
We need to figure out how we're going to do that.
We'll figure that out. So if you want to see the video, come out now because I think the audio may not be that loud.
So we've got one question for you. We've had about 7 or 8 viewers online, and we've got a question.
Sure.
ZFS latency with NVRAM arrays. Apparently we'll get that at some point here.
So the question is ZFS latency on NVRAM arrays, and
that's where it stops.
Right. Any other questions from the room, please? While I'm here, bug me. Any other questions? Yes? Yep.
How do you feel about overclocking and how it helps performance, or does it help at all?
It just depends on the workload, whether it's memory bound or not. I don't think it's going to help that many workloads. I mean, especially the workloads I deal with a lot are memory bound, not CPU cycle bound. Yeah.
Suppose it was memory bound, like a graphics program doing a bunch of rendering.
Yep.
Something like that. Do you think it might hurt, suppose, an Apple Mac computer running the latest operating system?
Yeah, I mean, that's tricky because when you're doing graphics, as far as I know, when you're doing graphics stuff, some of the algorithms can be CPU cycle bound, and some of them can be memory bound because you're pushing out frames so much. So it depends what sort of features they're doing like grid transformation, grid rendering and 3D rendering and things like that. So some of them can be very computationally expensive, but then you also have that memory rate of pushing frame buffers in and out. So you'd have to take it case by case and see what it was more bottlenecked by.
Well, I know Alienware talks about overclocking as something good for its gaming computers, but I never understood why that would be a good feature.
Well, the assumption must be that they're doing more CPU calculations than pushing memory. And if you're doing 3D rendering, which is what gaming does, they do a lot. It is computationally expensive to render those scenes. So that's what they'd be banking on.
I think overclocking is when a die is tested, and I just read on this, I haven't actually done it. My understanding is that when a die is tested, it's released at a certain spec, but in a lot of cases, because of defects and such, some dies will only maybe do 1.6 gigahertz, but other ones in the same release batch will go up to 1.8 or 1.9 before they start experiencing errors. So I think overclocking is basically, actually force feeding the CPU more cycles than what it's, standardized at, and having it actually push them out.
That's always been my understanding. A lot of CPUs are clock rated based on their failure and testing out of the same batch.
Yeah.
So we're going to try an experiment here with a question from the room.
Sure.
From the
A question from the online?
Yeah, I'm going to start now. Okay. We have this customer with a trading application, and the application is doing like 202 IOPS per 202 IOPS, and each IO is about between 5 to 12 Ks. The application is stored on a 9985V array with like 64 gig of RAM, and we're getting every now and again like 2 milliseconds for these writes, and the application is writing to a ZFS file system. From the array side, we're only using 10% of the available write cache. So I'm wondering what exactly could be causing this kind of high latency? Well, it's high for the customer because they're in trading.
Sure. So the question is, you're doing 202 IOPS of 5 to 10K. That's not many IOPS. Do you mean 202,000? So if it's 202 IOPS of 5 to 10 kilobytes, you can do the math. I'm surprised you'd use 10% of the Logzilla, but in case you were, if you're doing those write IOPS and you're using a Logzilla, then the reason would be you're doing synchronous write IOPS. And if you occasionally see latency jump up, there are a few things that could cause it. One of the main things would be these days, if you're writing to a ZFS share, if you're writing to a ZFS share with Logzillas, the performance should be good. That's why we have them. They have one of the advantages about SSDs is they have a very consistent response time. So you ask them, especially if it's a write-optimized SSD, you ask them to do something, they'll respond. Various reasons why you might get a slow response. There's a problem with the SSD. So SSDs that are write optimized, that have good write rates, depend on various technologies. Something might go wrong. We have seen SSD failures where the SSD device begins to respond with long latencies, and customers have had to swap them out. When that happens, however, it's not usually 2 milliseconds. They see it's more like 20 or even 200. So maybe that's not the case, but I'll just throw that out there. If you're running to a ZFS share, occasionally ZFS will flush out transaction groups. There's currently work going on. When you have big memory systems and it's flushing out a large transaction group, it will hold various locks. It will also have a thread that will step on CPU. It's running in the kernel scheduling class, and it can stay there and starve other I/O, like read I/O and other write I/O that's happening. So that's currently being worked on by Jonathan Adams, and I've actually mentioned it on my blog once before, calling it the picket fence, because in analytics you can actually see spikes of latency that happen between 5 and 30 seconds. So that's another reason why it may happen. So I'd say check out the drive. It could be this ZFS issue. dtrace will help you analyze further and see where the latency is actually coming from. Look at different levels of the stack. Is the latency coming from the drive, or is the latency coming from ZFS? Is the latency coming from NFS if it's NFS? And try to narrow down where that time is originating. There could be others. I'd have to think about it, but those would be the main ones at the moment.
And just to clarify, he's responded that no, it was only 202 IOPS, and they don't have a log device. But he's also said, great, thank you very much.
Okay. 202 IOPS, if you don't have a log device, it depends if the IOPS are synchronous or not. If they're read are by design usually synchronous. So for them to respond fast, you need to hit from cache. If they don't, then it's going to be the disk rotation, and it could be just a random disk I/O. For writes by default are asynchronous. They're going to be fast because they're just going to buffer. And it doesn't matter that you don't have a Logzilla. The spikes could be the CFS problem that's being worked on now, or some other kernel thread or some other event on the server that's just starving out CPU temporarily. And if it's synchronous writes, then it could be a random I/O to the disk, because you'll actually have to send it to the disk because you don't have Logzilla. And the 2 milliseconds could simply be that's how long the random I/O took. So what he needs to do is identify what type of IOPS they are and to see whether they're synchronous or not to disk. Another question?
Yeah, one last question. There's something I'm failing to grasp about the ZIL or slug or whatever you want to call it. What's the most commonly used? ZIL, right?
ZIL or slug, that's fine, yeah. Yep.
Anyway, the principle of using the slug is that the SSD is more consistent and faster than the back-end drive that you're eventually going to go and write the data to.
Yes.
That's assuming that have cycles to spare so ZFS can catch up between what's filling the ZIL and what's going to go to drives eventually. If I'm running full tilt,
yeah,
I'm going to overflow the ZIL at some point. How do I know? I haven't found a solution to know when am I spilling over the ZIL.
That's a good question. I've never been asked that before. It happens. So the question is, we have the ZIL, the ZFS intent log, can use a separate intent log, like write optimized flash, so that you can commit to stable storage and improve synchronous write workloads. For some other vendors I won't name, their equivalent has a small size, and they can overflow it pretty frequently, and that causes a bad performance problem. Once you overflow it, it has to go to disk to serve those synchronous write IOPS, and your performance can plummet. What we do is we try and give you, for this one vendor I'm thinking of, we give you 36 times the amount of space per Logzilla, per write optimized SSD, than they do, so that we don't have this problem. And when customers install multiple ones, you get to the point where you have hundreds of times more space than the competition for that workload. So my first answer is, just on the way we've designed it, it's unlikely. But I'm assuming that it's unlikely. With performance, you have to measure these things to be certain. So I don't know that I'd have to grep for kstat minus p, grep for if a counter gets bumped. If not, have a look in dtrace. So you should be able to, it's going to be hard because ZFS is complex because it's featured, but I'd write a dtrace script to identify that case where it had run out of space on the log device and then had to go to disk. You should see your latency go up if that happens.
You have to do more work. I mean, it's checking that flash device first. You have to see it full probably every operation, or once it's full.
I don't know.
Yeah.
Why does it check the flash device? Shouldn't ZFS keep track of how much it's written out and the volume? Why? So I don't know whether you know more about them than I do. That's why I'm asking. But
I'm just thinking. I mean, typically you're probably doing more work.
Once it fills up.
Well, I just want to know when it fills up.
Yeah, want to know when it fills up.
Because then I can throttle the load so that I allow you to do the
So
There should be a logical progression where it would check the SSD and return 1 maybe, and then go off the disk. So there should be some sort of call there that you could track.
yes. Now dtrace will definitely answer this. I'm just checking kstat to start with because if I'm an engineer and I'm writing that code, I'm probably going to throw in a counter just to troubleshoot this problem. To find things from kstat is kind of hard because kstat has 22,000 statistics and 0 of them are documented as far as I know. We've documented a bunch in Slice Performance and Tools, but it's kind of tricky. One of the problems behind documenting them is that while it's a great design, it doesn't have stability semantics like dtrace. So if you were to write documentation on them, they could change from one release to the next. There is a project going on in the open source community. I think it's Jason King who wants to bring stability semantics to kstat. Once that happens, we can then start to identify which of these guys are stable and write documentation for them, which would be fantastic. It's one of my pet dreams for a long time, documented and stable kstats. But if you're looking for random things in here, so I've just grepped for ZIL. There's a bunch of stats here for ZIL clean. ZIL LWB cache. That could be it, alloc fail. So yeah, I checked through these. You can find these in the code because these names you can grab through the code. Find that logical point. This is actually the source code to kstats, by the way, the source code. No, the documentation for the kstats, sorry, is the source code. So you want to know what one of these guys means, go to the source code for ZFS and look it up. And if it's in a block of code where the ZIL is overflowed, then you've found the counter. If that doesn't work, you're going to have to detrace it to get the answer. But it'll make an interesting script, and I'd like to see it.
Actually, on that thought, just using open-source.org to browse the ZFS code, there's a TX max type for ZIL transactions, which looks like it might be written out in the source code. So you can do a speculative detrace to find that, and when you see that transaction,
Cool. So someone has had a look on OpenSlice.org and has already found something. I'm just poking around with dtrace, seeing if I'm going to get lucky. Nope. So ZIL free, log block, ZIL create, ZIL empty, ZIL LWB commit writer, ZIL alloc, claim clean. So yeah, there's a bunch of things from dtrace. I can just look up the source code to see if any of these is going to give it to me in a return value. And hopefully it's just a one-liner in dtrace to tell you when you're bumping into it being full. If there is not a kstat for that, there should be. So that, see, the advantage with kstats is we can look at it after the fact. So if we suspect a customer has exhausted their ZIL, we can go up to, we can ask them, run kstat minus p grep and send us the output. And if that counter is non-zero, then they've exhausted the ZIL. So I didn't see it in kstat. So if it doesn't exist, it should. If it's not that alloc fail thing, if it doesn't exist, it should exist, so that we can troubleshoot it. Kstats are free and dtrace is not. That's correct. So that's why analytics tries to use kstat if it can, and only uses dtrace when kstats aren't there. Dtrace can be useful to you could prototype this statistic if the kstat didn't exist. Write the one-liner, run it on systems, use that to prove to the engineer this needs to be implemented. Like, this is information we want. Like, stop making me run a dtrace one-liner. I want this as a kstat so that I can see it after the fact.
I'm curious though, when it becomes full, is the algorithm to write to disk directly and ignore this? Ignore it?
Yeah, I believe.
But then don't you want to preserve, don't you want to get that stuff off of flash though at some point? It will.
I don't believe the ZIL gets stuff off flash ever. Right? It doesn't have to read what it writes because it's still in DRAM.
Yeah.
So that's one of the weird things about. It's not weird. It makes sense about the slog. Is you're writing it to the flash-based SSD for stable storage, but you don't have to read from it. It's still in DRAM. When you want to flash it to disk, you read it from DRAM and send it to disk. Why bother reading it from flash? You only read it from flash in the event of failure. So if the system fails, you lose the DRAM copy, so you have to get it from flash. So that's why read performance of them is not so interesting, but write performance is. The interface is stable. The statistics it provides are not.
What I'm thinking about is if analytics uses all the stuff and it's not necessarily stable, that could get really difficult.
Yes, that's a good point. Analytics does use a lot of the kstat stuff, and it's not stable. How we've mitigated that, we've written a test suite for Fishworks. It has over 1,000 tests, and they include a lot of little programs which will bump, which will do some event and make sure the kstat bumps. Sometimes it's hard to make sure it bumps the same rate of the event because there's other system noise, but so long as it's moving roughly in the right direction. So whenever I've put back new statistics into analytics, I've had to also put back the test suite that tests them. So we'll know when, actually, we'll know, this is what will happen. We'll know when a kstat breaks because if I don't spot it, because I'm using these things all the time, the test team based here in Colorado, when they run the test suite, it will fail. They'll email us and say this has failed. We run the test suite ourselves as well. So that's about testing.
Well, to get rid of the noise of the system, you can bump the events at regular interval and then filter with a Fourier transform.
Yes, I've always wanted to do that. I've never, I've never had the couple of hours to spare to sit down and like fire up MATLAB or something and do that. But one of the I don't know where I first read about this, but someone was doing, especially with kstats, if they're undocumented. And I used to do this a lot actually I used to do this myself as a customer before I had access to the SLAS kernel. I had kstats with no documentation. So how do you figure out what these guys do? Well, you write experimental tools. Do 10 megabytes of malloc. What moved by 10 megabytes? Actually, usually do 23 events or 17 events, some prime number, and what moved by that prime number. The problem with that is there's a lot of system noise that interferes with it as well. So I heard someone had a great solution to this, and that was bump the statistic not by, say, a prime number, 23, but bump it with an interval of 23 seconds. And then do a fast Fourier transform, like gather the statistic over a period of hours and do a fast Fourier transform over all the statistics and look at the frequency domain and see what has a spike at 23 seconds. So I'm really keen to do that one day, and I've never had the chance to do it, but.
The only way to not knowing which metrics you're impacting to know which you are going to impact is by observing.
Yeah, you can read the code, but just by observing, Yeah, it's a pretty good way to do it. I want to add fast Fourier transforms into analytics for the sun storage systems. I went back to Australia a few months ago, and one of the only things I did was bring back my university textbooks from both math and computer engineering that had fast Fourier transforms, because I did signal communications and they teach that stuff. And so I now have the textbooks I need to refer to implement this, but I want to put fast Fourier transforms into analytics so that if you're looking at, say, CPU utilization or disk I/O, you can look at the frequency domain and say, oh, I'm actually getting a spike of disk I/O every 5 seconds or every 55 minutes, something that would be difficult to spot otherwise. So.
One thing that would be extremely useful would be, and that's something that we're working on in my team, is a correlation engine that correlates different metrics and their spikes. So we can see, when there's a spike in CPU, we can see, oh, there's a spike in I/O as well, and there's a spike in network. And correlating is just a great way, not knowing what's going on, to try and see what are the different components of outliers, because we're always looking at outliers for response times.
Yeah, you've mentioned correlation, and correlation is really, ideally, you would associate the events together, write a dtrace script that was able to associate the disk events with the CPU events and put it all together so you wouldn't have to play this correlation game. But in practice, I'm just trying to find an example. In practice, it's really hard. If you're looking at resources that are in completely different subsystems in the kernel, trying to actually associate all the information properly can be a lot of work. Sometimes it's easier just to eyeball it and say, this bumped at the same time that bumped. We do that in analytics all the time by plotting the data side by side. So these have a fairly good correlation. Actually, that wasn't too hard. I'm only comparing NFS operations with device bytes. But I can go over any part of the stack and make sure that they match. Ooh. Okay, it's the same thing, same thing. CPU percent utilization and network device bytes has a very direct correlation because my eyeballs tell me that. And the same with NFS-v3 operations. So yeah, I'm a believer. I used to be a text-based person until analytics and GUIs showed us the value of our eyeballs and visual recognition. But it's really cool. Because I know this sort of dtrace script to associate all the layers together, it's hard. It's so nice to just graph them and say, the graph is the same. I don't need to write that dtrace script. These events are related.
Yeah, eyeballs are great, but they only catch what they see.
Yes, yep. So if you want to do that programmatically, that'd be interesting. Difficult, but interesting.
Well, the thing about the Fourier or the Fourier transform is that you could actually see multiple frequencies in the same, in the same area. So you might have one hotspot, but it will actually find out within where you're running through that, you actually get multiple matches, at the same time.
Yeah.
That's right. And that's what's needed, so that we actually can find multiple places, harmonics or whatever.
Yeah.
In the data. So,
you're saying two frequencies that happen overlay at the same time producing conflict.
Or just two problems, one screenshot.
Yeah.
Yep.
Yeah. It's basically they're similar data, but they're in different places, basically.
Yeah.
Yeah. Different frequencies. So that you're measuring the same data, but you have different aspects of it in different places or different frequencies.
No, I'm keen to do it, and like I said earlier, now that we've done heat map analytics of latency, there's all sorts of unknown unknowns that are now known unknowns, and I expect it will be the same with Fourier transforms. There'll be a whole bunch of things we just didn't even know were problems that will just jump out in the frequency domain, and will be interesting. Are people asking questions online?
No, that's only the stream is going to end in 3 minutes.
Stream's going to end in 3 minutes.
I've done it for 3 hours.
Any other questions? You can just hit me afterwards for questions, and I'll play in high quality. For people who haven't seen it.
Sorry for screaming, it's very loud in here with the air conditioners and servers all around me. We just made an interesting discovery and we thought we'd show you straight away. So over here I'm measuring disk I/O operations broken down by latency. I've also drilled down to disk I/O operations taking at least 520 milliseconds broken down by disk. This is using T-Trace so I can do performance analysis of disks. I'm applying a write workload to 2 JBODs, which are over here. The lights are blinking on these JBODs because they're doing work. What I'm going to do is not recommended. This is not supported. Do not try this at home. This is real. What we're looking at here is the effect of disk vibration. Vibration is a serious issue, and we can see the effect here that it's caused. So here, the latency for the disks that are under the workload has gone up. Here I can see which disks have now had I/O operations longer than 500 milliseconds, and I can find out that they belong to the JBODs I was just shouting at. So, amazing stuff. This has been made possible by analytics from Fishworks, which lets us look at things we've never seen before. This latency, high latency caused by vibration is a real issue. You've seen it. It does exist. Just don't let Brendan shout at your disks. That's right. Don't shout at your JBODs. They don't like it.
And of course, there's lots of YouTube inane comments about this. Lots and lots of comments about this. Has anyone parodied this? Not yet. Hopefully not that close and that loud. Cool. I asked Brian before he videoed it. We didn't rehearse. It's like, what do you want me to say? He's like, just introduce the problem and say it. One take on YouTube straight away. That's how it came about. All right, thanks guys, and I'll switch off the mics and you can hit me up afterwards as we grab pizza and